Okay, let's dive right into this. Welcome, everyone, to today's Executive Explainer. We're setting the stage for a high-level status review of what is, without a doubt, humanity's most distant active asset, Project Voyager 1. We're going to break down its initial deployment, look at its current operational constraints, and really dig into the incredible data it's still delivering to us today. Just to quickly align on our agenda for this review, we'll be tracking 4 key project milestones. We'll start with the project's inception and scope, then move on to its successful deployment into interstellar space. After that, we'll review our current operational constraints, and finally, we'll wrap up by forecasting the mission's long-term legacy and future. All right, let's get into it. Starting off with Phase 1, let's look at the project inception and the overall scope of the mission. To really understand our current operational status, we've got to first look at the initial roadmap. And this timeline brilliantly illustrates the sheer scale of the operational window we're managing here. Think about this. The project launched way back in 1977. Fast forward to present day, and this asset is literally still out there conducting active operations in interstellar space. Looking ahead, we're projecting a few more years until total power depletion, followed by a long-tail trajectory of drifting through the galaxy for millions of years. Reviewing this timeline doesn't just show us that Voyager 1 is the most distant human-made object ever launched, it really highlights an absolutely unprecedented level of engineering resilience. I mean, we're talking about technology from the 1970s. This thing is operating with a vastly less computing power than the key fob used to unlock your car. Yet, it has survived decades of intense radiation and near absolute zero temperatures, all while successfully executing its primary mission. It's a massive win. Moving right along to Phase 2, reaching interstellar space, or what we can consider our primary deployment zone. 25 billion. Since its launch, Voyager 1 has traveled more than 25 billion kilometers from Earth. Or, for those of us operating on the imperial metric, that's over 15 billion miles away. It is absolutely vital that we anchor ourselves to this unimaginable scale. This isn't just some off-site deployment a few time zones over. This is an asset actively functioning in an entirely different region of the cosmos. The extreme durability required to maintain an active, working project at this kind of distance is simply staggering.
Now, to fully grasp the so what of being 25 billion kilometers away, we really need to define our project boundary. The spacecraft successfully breached what astrophysicists call the heliosphere. Basically, that's the sun's protective bubble. It is the literal boundary line marking the edge of our solar system. Voyager 1 didn't just reach that edge. It completely crossed the boundary. It successfully pushed out of our solar system and into true interstellar space.
So, what exactly are our active deliverables right now? Well, out there beyond the heliosphere, the spacecraft is still hard at work. It's actively studying the environment between the stars. The data it's collecting is directly helping scientists learn about the very edge of our solar system and the interstellar medium beyond it. The asset is actively yielding critical intelligence from a region of space that humanity has literally never successfully probed before. It's a real game changer. Which brings us to Phase 3 of our review, current operational constraints. Let's talk about the unique logistical challenges of this unprecedented deployment. Let's look at how we're actually retrieving those deliverables. Despite that massive 25 billion kilometer distance we just established, the spacecraft continues to successfully beam data back to Earth using a powerful radio signal. The infrastructure here is incredibly robust. Honestly, it speaks volumes about the initial project specifications. It's those original specs that allow the transmission of scientific data across the vast empty void of interstellar space day in and day out. Now, what's really interesting about this metric is the number 23. Because of the sheer vastness of the space involved, that powerful radio signal takes over 23 hours just to reach us here on Earth. And remember, that is just for a one-way transmission. I think anyone who has ever managed a distributed team can appreciate this kind of extreme communication latency. You could really say Voyager 1 represents the ultimate remote work communication challenge. I mean, when your remote working distance is over 25 billion kilometers, you can't exactly expect a quick turnaround on a system ping. The fact that we're maintaining a continuous, albeit highly delayed, data stream under these extreme latency conditions is a massive operational success. It's a true testament to the long-term durability of the systems we put in place decades ago.
Let's move on to our final section and see how all of this builds into our end-of-life projections. We'll be looking at the mission's legacy and future.
Let's compare the near-term and long-term outlooks for the project. On the near-term side, our operational status shows that Voyager 1 is expected to keep communicating for just a few more years. Eventually, the onboard nuclear battery is going to run completely out of power, and those active data transmissions will permanently cease. But we have to compare that against the long-term asset legacy. Even after the power finally depletes, the physical asset itself doesn't just disappear. It's going to continue drifting silently through the galaxy for literally millions of years. So the active project phase will end, but the deployment itself, that's practically permanent.
So the crucial takeaway here is this. How do we even begin to measure the final success of an endeavor like this? I want to leave you all with a profound question to think about. What is the ultimate ROI, the true return on investment of a project that is going to outlast the very people who launched it, outlast the civilization that built it, and drift through the galaxy for millions of years? It's definitely something to ponder as we wrap up this explainer on humanity's most distant and honestly most ambitious endeavor. Thank you for joining me.